Hello, welcome back. In this video, we'll be talking about new coordinate systems, namely polar, cylindrical, and spherical coordinates. So a coordinate system is pretty much a way to give names to points either in the plane or in three-dimensional space. You're actually already familiar with a way of doing this using x, y, and z as coordinates to name points. So what we're going to be doing here is exploring a couple different ways to give names to points. If that doesn't make sense, you'll see what I mean as we go along. So let's start with what we're used to. And the thing that we're used to, I'm going to call it rectangular coordinates. You might also sometimes see it called Cartesian coordinates. But it's what we mean when we say like the x and y coordinates of a point in the plane. So here's x and y axes. And if we have a point, say here, for this point is the point, how about 4, 2? Then we have an interpretation of what these numbers mean. And when I was saying before, like giving names to points, like this is the name of this point, 4, 2. And the way we interpret this is, well, if we wanted to find this point, we would move 4 units along the x-axis and 2 units along the y-axis, and we would have located this point. And the important thing is that every point in the plane has an x and y coordinate, and actually every different combination of x and y coordinates gives you a different point. So again, this is rectangular coordinates. You can kind of see why it might be called rectangular coordinates. I've kind of drawn a rectangle here just in my diagram. We'll see that the way that these coordinate systems are named are sort of suggestive about what they are best used for. So now I'm going to do a quick review of polar coordinates. If you've never seen polar coordinates before, this is probably not the best place to learn it for the first time. There's a handout on Canvas that you can go look at that will kind of run you through the basics and tell you what polar coordinates is all about. I'll also put in the description of this video on YouTube some links to some Khan Academy videos that you can go watch if you want a more thorough introduction. So anyways, if we want to give names to points using polar coordinates, we're still going to draw these axes. And I'm not going to call it the x and y axis, strictly speaking. I mean, you can still label them x and y. If we want to get technical, sometimes the horizontal axis here is called the pole, and the vertical axis isn't called anything. So if we have a point, maybe it's that same point, we're going to give it 2 numbers to specify where in the plane it is, but it's not going to be horizontal and vertical displacement anymore. Instead, we're going to give this point 2 numbers called r and theta. What those 2 numbers are is r is the distance straight to the origin. So it's this length here. And theta is, we've drawn this dotted line here. Theta is the angle that this makes with the positive x-axis. So I'm going to write a little summary here. R is distance to the origin, and theta is the angle with the positive x-axis. I'll note that something that we're going to want to be consistent about just for our course, this isn't across the board always the way it's done, but we're going to always say that r is bigger than or equal to 0. Some textbooks let r be negative and kind of try to interpret what it means to have like a negative distance. We're not going to mess with that. We're just always going to say r is distance to the origin, and as a distance, it's always bigger than or equal to 0. One last thing I'll note is that converting between different coordinate systems is sometimes useful. If we know the polar coordinates of a point, if we know r and theta, we can compute x and y by, well, we can kind of imagine drawing in a right triangle here. The length of this vertical segment would be y. The length of this horizontal segment would be x. And using the fact that this is a right triangle and doing some trigonometry, you arrive at x is r times cosine theta, and y equals r times sine theta. Again, coming just from relating, the cosine of this angle to the length of the adjacent side and the hypotenuse of this triangle, and the same thing for sine. Okay, moving on, we're going to talk about cylindrical coordinates. So whereas polar coordinates is a new way to give names to points in the plane, cylindrical and spherical coordinates are going to be new ways to give names to points in 3 dimensions. So cylindrical and spherical are both 3-dimensional things. And I'll draw a similar picture to try to describe what all of the cylindrical coordinates mean. So now we're drawing 3 axes. So let's say we have a point here. Now, normally, again, we would use rectangular coordinates to describe the x, y, and z coordinates of this point, which would reflect how far you move in the x, y, and z directions starting from the origin to get to this green point. But if we're going to use cylindrical coordinates, what we're going to do is essentially turn x and y into r and theta in the same way that x and y turned into r and theta for polar coordinates. And we're going to leave the z coordinate the same. So here's what I mean by that. We're going to give this point the name r, theta, z. And to measure these three values, from this point, we'll draw a vertical line down to the xy plane. So this blue point here is on the xy plane. Then, since this is a point in the xy plane, we can measure its polar coordinates like we did before. So draw this sort of line here from the origin in the xy plane to this blue point. Compute its length, which again I'm going to call r. Measure this angle here made with the positive x-axis, which we're going to call theta. And then for z, well, the z coordinate of this point is the same as it would have been if we were using rectangular coordinates. So it is really just measuring displacement along the z-axis. So before r was in polar coordinates, it was distance to the origin. But it's not really distance to the origin now, right? The distance from this green point to the origin is kind of along this line like this, which is not really what this distance is. One way to think of it is its distance to the origin once you kind of drop the point onto the xy plane. That's a little bit wordy. So a way I like to think about it is, well, another way to draw a segment with the same length here is to draw it up in the same horizontal plane. So let's draw it here in pink. So I'm drawing a line. This line goes straight to the z-axis, and it's parallel to this one in the xy plane. So the length of this is also r. And so sort of a consequence of this is that we can say that r is the distance to the z-axis. Just like in polar coordinates, we're always going to say that r is non-negative because it's measuring a distance. For theta, before we were measuring the angle made with the positive x-axis. That doesn't super make sense for a point that's floating up here where this green point is. You could think of it as it's the angle with the positive x side of the xz plane, but that's also sort of wordy. The way I like to write this is theta is an angle that measures rotation around the z-axis. So as you rotate counterclockwise around the z-axis like this, your theta angle is increasing. So I like to say it like that. You might want to come up with your own description. If you liked thinking of it as an angle with a half plane here, that's completely fine. And the last thing is z. Well, z we're already familiar with from rectangular coordinates. This is essentially vertical displacement, measuring how far above the xy plane the point is. Above or below, right? If it's below the xy plane, then z is negative. All right, one last thing before we move on here. Just like before, we want to sometimes convert between different coordinate systems, meaning if we know the cylindrical coordinates r, theta, and z of a point, it will sometimes be useful to us to be able to figure out its x, y, and z coordinates. So just like we did for polar coordinates, and I'm not going to actually do this. I'm leaving this to you to figure out. If you know r, theta, and z, I want you to try to come up with formulas for x, y, and z in terms of r, theta, and z. You can call these like identities, like coordinate identities. So this is for you to try on your own. I'll give you a hint. If you already know r, theta, and z, then you can compute z by just putting a z here. Okay, so that was the easy one. The hard ones are for you to figure out. If you know r, theta, and z, what are x and y for this point in three-dimensional space? Okay, for spherical coordinates, I actually want to do just a little bit of motivation, because the way that spherical coordinates works can be a little confusing at first. It's another way to give names to points in 3 dimensions. But the way it works should be familiar if you've ever thought of latitude and longitude. So here is, just to start, a picture of planet Earth. You can tell because I've labeled it as Earth. Now, if we have a point on Earth, so here's this green dot here is a point on the surface of the planet Earth, and we want to give a name to this point. Well, we don't use x and y because x and y are planar coordinates. They're used for flat things, and the Earth is not flat. So what instead we do is we use latitude and longitude. And to do that, we draw in two kind of important lines here. So the first one is this orange line. This is the equator, which actually isn't made up, right? The equator is sort of determined by the way the Earth rotates around its axis. But anyways, if we want to compute the latitude of this point, it's an angle. If we're over here on this green point and we want to compute the latitude, we draw, this dot is at the very center of the Earth. So it's inside this sphere at the center. And we sort of draw these kind of reference lines here and down to the equator here and then over like this. And we compute this angle here. And that is the latitude. So next, if we want to compute, so that's one number that tells you where this point is, but to really nail it down, we need another number, and that number is the longitude. So there is another curve on Earth like this. This is called the prime meridian. This line was invented by humans. There's nothing geologically intrinsic about this, but we just had to pick a place to be 0 longitude. So to find the longitude, we kind of draw this dotted line here that goes to the prime meridian from the center of the Earth. And now with this same reference line that was drawn to the equator, we kind of draw in this horizontal angle here. And that is the longitude. Okay, so the point of this was to say that we are used to measuring locations on a sphere using two angles, right? These are both angles. Now, there's only two angles here. There's only two numbers because we're measuring position on a two-dimensional object. The surface of the Earth is two-dimensional. If we want to extend this to a way to give names to points in three-dimensional space, maybe it would help to think about how we would give a location to, say, a satellite that is orbiting Earth. If there was a satellite over here, we could still sort of use latitude and longitude, except we would also need an additional piece of information, which would be how far from the center of the Earth is that point. It's going to be a way to designate locations in three-dimensional space by specifying two angles, which are sort of like latitude and longitude, but not exactly, along with a distance, which will be a distance from the origin. So to show you what exactly those are, I'm going to draw a similar picture to the one that I did for cylindrical coordinates. So let's say we have a point that's in three-dimensional space. So what we're going to do is specify the location of this point using three numbers. Those three numbers will be called rho, phi, and theta. So I'll put, before I tell you how to measure them, I'm just going to write them down so that you can see. This one that looks like the letter P, it's a Greek letter R, written RHO, pronounced rho. The second one is an angle. It's like a horizontal theta, sort of. This one's called phi, P-H-I. And theta we all know about already from polar and cylindrical coordinates. Okay, so how do we compute these three numbers? Remember, two of them are going to be an angle, so phi and theta are the angles, and rho is the distance. So to compute that distance, we draw a line from the point in question straight to the origin, and we're going to measure its length, and that is going to be rho. So rho is distance to the origin. And now it's worth noting that this is analogous to r from polar coordinates, but not the same, because we're measuring distance in three-dimensional space. That said, we have that same convention that rho is always going to be bigger than or equal to 0, because it is a distance. Next, to figure out what phi is, we are going to look at this little reference dotted line that we drew here to the origin and compute the angle that this line makes with the positive z-axis. So this is going to be phi, this angle here. And the way I like to write it is just by saying it is the angle made with the positive z-axis. So I'll tell you a couple more things about phi in a second, because there's some nuance there. But lastly, for theta, well, actually, theta is the same angle that it was for cylindrical coordinates. So to compute it, we'll draw this dotted line down. So we'll drop this green point down to the xy plane, and then draw this sort of reference line here, and compute the angle made with the positive x-axis. So again, you can say theta is the angle that you make with the positive x-axis once you project down into the xy plane, or it's the angle made with the positive x side of the xy plane, but that's kind of wordy again. Or you can say it the way I like to say it, which is just saying that it is an angle that measures rotation around the z-axis. Going back to phi for a second, it's important to note that the angle that we're measuring here is always the one with the positive z-axis. So in other words, if I have a point down here, and this point is below the xy plane, so I'll kind of indicate that by saying if we wanted to draw the projection onto the xy plane, we'd be drawing a line segment up. So this blue point is also on the xy plane, like this one. And this green thing is vertically below it. Anyways, if we wanted to measure the phi for this point here, we would draw this same line to the origin, which I'm doing in pink here. And the angle that we would measure would be the angle still with the positive z-axis. So we'd be measuring this angle here. So you can kind of see that the value of phi for points that are below the xy plane, the value of phi will be bigger than 90 degrees. And actually, now that I say 90 degrees, I should note that for all of this, we tend to use radians instead of degrees. So really what I should have said is phi is going to be bigger than pi over 2. So the next thing I'm going to say takes a little bit of time to convince yourself of. I'll give you a link to a Geogebra applet towards the end of the video that will hopefully make it a little bit more clear. But since phi is always measuring the angle with the positive z-axis, there are limits to how big and small phi can be. The smallest phi can be is when the point is exactly on the positive z-axis, in which case phi will be 0. And the largest phi can be is when the point is on the negative z-axis, in which case the angle would be measuring all the way from the positive z-axis to the negative z-axis, which would be an entire 180 degrees or pi radians. So phi is always an angle between 0 and pi. It's also worth noting that we don't put any similar restrictions on theta. We just say theta can be any angle. It can be negative if you want like negative pi over 2 to be like over here for theta. That's fine. There's no restrictions, but phi is always a number between 0 and pi. Okay, one last thing. Just like with the other coordinate systems, sometimes we're going to want to convert between them. And we only tend to do this conversion one way, which is if we know the spherical coordinates of a point, if we know rho, phi, and theta, then occasionally we're going to want to be able to figure out what x, y, and z are in terms of rho, phi, and theta. So I'm going to leave this as another exercise for you to do. I want you to figure out a formula for x and a formula for y in terms of rho, phi, and theta. But just to show you what I mean, let's compute z in terms of rho, phi, and theta. And well, z could be thought of as this distance from the green point here down to the blue point in the xy plane, right? It's the vertical distance. You could also think about it like it's the distance along the z-axis. If we draw kind of a dotted line here, then this distance is also z. So what you end up with, and hopefully my picture can convince you, is there's a triangle here that you can use to figure out what z is in terms of rho, phi, and theta. And it's a right triangle. There's a right angle in this top left corner. So what you have is a right triangle whose hypotenuse has a length of rho. The adjacent side to this angle measured phi is z. So just off to the side, we'll know that the cosine of phi is going to be the adjacent length over the length of the hypotenuse, so z over rho, meaning if you wanted to use this to find z, you could multiply both sides by rho, and then you get z is rho times the cosine of phi. So, okay, just a hint to figure out what x and y are. You can use this same triangle, and note that the length of the opposite side is r from cylindrical coordinates. So that's the hint. Use this triangle to relate r to theta and rho, and then if you know from the previous exercise about cylindrical coordinates how to write x and y in terms of r, then you'll be on your way. So those go here. Okay, so last thing, I made this app in Geogebra just for you to hopefully be able to explore a little bit more geometrically what's going on with both spherical and cylindrical coordinates. This isn't the final version of it. Hopefully I'll be able to improve some of the way the text is laid out and the clarity by the time you actually see it. But the point is, you have this point here. This is the point that kind of we've been drawing a picture of the whole time. And you can move it around. If you click it, you can move it horizontally. If you click it twice, you can move it up and down. And what I want you to do is go in and just like see what's going on here. Like this is the 3D version of that picture that I've been trying to draw for you for both spherical and cylindrical coordinates. These line segments are labeled so that you can, if you can see it in the video, there's an R here that tells you the R value, like the distance to the Z-axis of this point. And as you move the point around, that will change depending on how you move the point. And there's that angle phi here between this like reference line with length rho and the positive Z-axis. So you can kind of explore how that works. Something I didn't mention when I was talking about it earlier, but the value of phi doesn't change if you rotate around the Z-axis. So even for a point over here that lies above the third quadrant in the XY plane, the value of phi is still this angle to the Z-axis. It doesn't become like negative. It doesn't swing all the way around. It sort of stays constant as you rotate around the Z-axis. So anyways, I hope that helps you see a little bit more into the geometry of what's going on with these different coordinates, and maybe will help you start to see sort of the relationships between them. All right, so that brings us to the end of this video. I left something really big out of this introduction to cylindrical and spherical coordinates, which is, what's the point? You know, like, what are we going to use them for? And the answer is, you'll see. As you use them and as you get familiar with what they mean and the geometry behind them, you're going to start to see that cylindrical coordinates is useful for describing things with like cylindrical type symmetries. It's useful for things that have rotational symmetry around the Z-axis. Similarly, spherical coordinates is really useful to describe objects that have kind of rotational symmetry around the origin, things like spheres. One of the things you can start thinking about now is how you would write an equation to describe, say, a sphere using spherical coordinates. Right? In rectangular coordinates, it's x squared plus y squared plus z squared equals the radius squared. But if you want to do something using just rho, phi, and theta, you can start thinking about like what would be different. And it turns out it's a lot simpler because spherical coordinates is made with spherical geometry in mind. Okay, so good luck with all of that practicing, and I'll see you in the next video.